So welcome to the first proper lecture on image processing. In this lecture, we're going to give you an overview of some aspects of biological vision, but we're going to do this in quite a shallow way. And this is kind of background knowledge to help you understand image processing a bit better. So we start off by thinking about how we capture visual information. And of course, we capture visual information through the eyes. And the eye structure, I'm sure you've all come across before. And the sensitive part of the eye, so the bit that captures the information, um, is the retina, which of course lines the back of the eye. And the location of highest spatial resolution or highest spatial acuity is found in the foveal region here, which really represents quite a small fraction of your entire visual field in each eye. Now, there is a temptation to think about the eye and the retina in particular, as simply being a camera. Simply like the sort of camera you might have on your mobile phone or a digital camera more generally. But actually, there are some hints that the eye should not really be treated merely as a camera. And indeed, perception itself is the way that we perceive particular spatial structures gives us a hint that there is something going on apart from simply sensing position or intensity or color as a function of space in a strictly linear fashion. And one of the primary places that we encounter, or one of the first hints or most obvious points at which we might suspect that there's something more to vision, that pun intended, that meets the eye, is through visual illusion and the occurrence of visual illusions. So one of the best known visual illusions is really very simple. Is known as the Mach band effect, and it's illustrated by the image shown here. So what you see here is a series of bars of intensity which are increasing in steps. So if you were to plot a line or plot a graph of, let's say, on this axis you have intensity, so on the vertical axis you had intensity, and on the horizontal axis you had spatial position running through the image from left to right, then what you would see is a series of steps as the intensity goes from 0 up to maximum intensity. But what we perceive, and I think you will very quickly become aware of this, is a sort of a graded intensity across these bars. So rather than the intensity being something like a step, or a step going this way, you might perceive that the intensity feels a bit more like it's going up and then sort of scalloping, and then going up and then sort of scalloping like that. So it's a scalloped appearance. So it's kind of bending downwards in the middle of each bar. And that isn't what's happening. I mean, if you were to actually plot the pixel intensities as a function of spatial position, you are indeed simply going to see steps. Okay, so your visual perception is throws something else into the mix. So what is the cause of this? Well, we're not going to go fully into the cause of it, but what I will say is that one of the first explorations of this phenomenon has been explained by looking at the retina and trying to build a model of the processing that goes on within the retina. Now, I've got some supplementary notes in which I'm going to talk about this a bit more, but for the time being, let's just say that what the retina might be doing is in some way introducing this sort of bendy effect in the intensities. Now, why is that happening? Well, it turns out that one of the very, very important visual cues that we have about spatial structure of things in the real world comes from the location of discontinuities in intensity as a function of spatial position. And so if we move on to this slide here, so I've skipped a slide, but I'll come back to the other slide in a second, then this is perhaps one of the most dramatic demonstrations of that principle. So on the left-hand side, we have what appears to be a slightly dark gray panel flanked by two lighter colored gray panels. In fact, the intensities across this rectangle look a bit more like what we show in figure B. So it goes from 150 on the left-hand side to a value that's a little bit higher than 150. It's about 152 or so. And then plummets down. So we've got this very strange, odd discontinuity. But in this location and in this location, the intensity values are actually the same. 150 here, 150 here, and also 150 on this side. Yet, because of the particular shape of these discontinuities, what we perceive instead is that the middle rectangle has a lower intensity than the two flanking ones. So this is a quite surprising demonstration, and it's known as the Craig-O'Brien illusion. Now, coming back to this notion of brightness, so I've now gone backwards in the slides. There is a phenomenon known as, which is a bit better known, which is simultaneous contrast, which is if you look at two rectangles which have exactly the same intensity, but which are displayed against different colored backgrounds, then you get the impression that one of these rectangles is brighter than the other. Now, this effect makes it difficult to give an absolute judgment on the brightness of any structure in the real world, and that's because our perception of brightness depends very much on what the rest of the background looks like. So moving on a bit further, it's kind of, so you can make a model that describes the mapping between the spatial inputs to the retina and the outputs of the retina, which approximately can explain the idea of simultaneous contrast, or the concept of the inability to determine contrast, and also even to some extent to explain that perception of the darker, or the scalloping effect that we saw, the so-called Mach band effect we saw in the first illusion, which is this one back here. Okay, so you can make a simple computational model that explains this, and that computational model makes use of something called spatial convolution. However, there are other things that are going on, and probably one of the most dramatic illusions that I've come across, so I think this is my favorite, yeah, it's probably my favorite visual illusion, is this one here. And this is by Ed Adelson of MIT. And what you have here is a sort of what seems to be a three-dimensional checkerboard, so it's fairly easy to figure out what this is. But then we've got this shape that's plonked in the middle of the checkerboard, and we have a shadow that is cast across the board. Well, if you were to crop this image out and stick it into a drawing package, and then grab some pixels from this region, so let's say take a crop of region A, and then go back to the original image and take a crop of region B, and then put them side by side, you will see that the pixels in region A and the pixels in region B have exactly the same intensity. In the image, they've got exactly the same values, and so the perception that B is brighter than A is entirely due to your higher levels of visual cognition, recognizing that there's an object here that's casting a shadow across the board, and that B, or the square belonging to B, lies in that shadow, whereas the square belonging to A is outside of that shadow. Okay, now it really is recommended that you try doing this yourself, because it is pretty stunning to when you see that the pixels around A in this square and the pixels around B in this square have exactly the same intensity. It's pretty surprising. I mean, it's astonishing. So what that tells you is that your perception of the world really can't be trusted when it comes to making judgments about absolute intensities, and in some cases also about colors. So, but this is something that we'll explore later on. Okay, now we pause here, and I suggest the next set of slides you look at should be the supplementary material, which covers a bit more about biological vision from the perspective of neuroscience and introduces a bit more concretely the notion of receptive fields, both in the retina and also in the primary visual cortex.